everyone. Welcome to IoT Data X-ray, part of our oil and gas data science series on Digital Hub. Before we get started with the presentation, please notice our legal disclaimer. Material presented here, including but not limited to text, images, and codes, are subject to Digital Hub terms and conditions and are for demonstration purposes only, and may include future product features and plans. Sharing, copying, reproducing, and modifying them in any form requires Integra's permission. I am Hoda Rezai. I'm your host today. And today I have Babak Shafi, our founder and EVP, and Sylvia Lee with me. And with that, I'm going to hand it over to Babak for an introduction. To you, Babak.
Thank you, Hoda. Good day, everyone. Thank you for joining this event. If you have joined our previous events, we're making some changes to the format of the event, and we really love to hear your feedback on how this format is working. In the previous events, we were more hands-on and detailed into the notebooks and actually executing the code. In this event, we're trying to focus on the methodology and the process to get to that insight from our sensor data. So we'll see how this works. We'd love to hear your feedback at the end. There is a survey, 2 questions you can fill out to let us know. Integra, if you haven't heard about Integra, our mission is to reduce barriers to adopting AI and ML in oil and gas industry through innovative solutions and agile delivery. Our value proposition is around ability to deliver end-to-end data analytics solutions. Is it from a strategy and the concepts all the way to development of the solutions, or if you already have solutions, optimizing the existing solutions. And overall, our services and capabilities fall into 3 core areas, which is our expertise in oil and gas. So we've been in oil and gas for a long time and run data for 20 years. We have a really good understanding of operational issues in the industry, as well as the data format, the data challenges, and the types of analytics can actually drive insight for your organization. Our services can be as simple as strategy and consulting, helping our customers get on the journey of AI and ML on the right path, and help them along the way to save a ton of money in terms of how they execute, how they successfully arrive at the path that they want to reach. Also helping some with business case development. So if you have ideas and you don't know how this will actually impact your business, we have ability to come up with metrics and KPIs that demonstrate, for example, if you do a pump failure use case, or if you do an energy management use case, how would it impact your business? We offer also staff augmentation. If you already have a team and you just need additional hand, we offer that, as well as our own platform, which is intended for organizations that they need to get up and running quickly and need a data science platform. Our methodologies, as you will see part of it today, are based on end-to-end repeatable, scalable concepts. For a lot of the use cases and solutions that we offer, we have developed accelerators that allows us to quickly help our clients successfully execute on an initiative. Can go to the next slide, please. Just a little bit more on that accelerator. Again, focus on different areas. So predictive maintenance, pipeline integrity, production optimization, process optimization, health and safety. We have accelerators for these types of projects, as well as the data sets that are on Azure, on AWS, or maybe local in your Historian or Google Cloud. These accelerators enable us to quickly access these data sets and enable a project, as well as the workflows. I will go through some of these. For some of these capabilities, we have actually developed actual workflows. So when it comes to gas well flow forecasting, or sensor data analysis, or power plant, if you have a power plant, and you're looking for alpha predictions, or you're trying to come up with trading recommendations, we have accelerators that actually do that type of work. And in terms of the technology and the techniques, similar to many other capabilities, we have the ability to simulate an outcome, to predict an outcome, use deep learning and neural networks, help you with data engineering. And most of our initiatives, at least this year, is the case, will be supported with government funding. So if you have an idea and if you have a use case and you would like to try the use case, and as long as you're in Canada, there is government funding that will support the project. Next slide, please. Digital Hub platform, a little bit, around Digital Hub and what it is. It's intended to accelerate your path to data insight, and enable you to with machine learning, automation, big data, a lot of the capabilities. So almost every capability that you would need to create a project is in Digital Hub. And the idea is that it will give you a ready to go platform for you to optimize your project. So you don't have to spend too much time on the IT and the technicality of your setup, and focus on the actual delivery and focus on the value generation. So think of Digital Hub as a toolkit that will give you alerting, machine learning, anything that you need to quickly develop your ideas and your solutions. Next slide, please. So who is it for? Again, our focus on oil and gas, but really it's a data science platform we can use in any industry. But then it comes to oil and gas, our focus is on operators. So if you're in upstream, midstream, or downstream, and you're operating, you have operating assets, it can support with generating ideas and innovating in that space. If you're a service provider like drilling company or well servicing or fracking, you could start to leverage Digital Hub in order to create these digital services for your clients. You probably have lots of access to lots of data, and you can enhance and create these new services on top of data that you already have access. Some of you who are in this service provider category are already probably getting. The idea here with Digital Hub is to accelerate that technology path for you. In terms of large organizations that already have a platform, that have already established programs and strategies, there is not enough data scientists or engineers to centralize everything in one place. So most of our organizations are thinking about center of excellence or community of practices or systems of innovation, a way for the organization to quickly deploy and enable a large number of users who can generate ideas, who can generate insights. And that's the role that Digital Hub can play. And if you're a small or mid-sized enterprise, it can be our project accelerator. So if you think about production optimization, energy optimization, all of these different use cases, there's accelerators for these, so you can leverage them to quickly get up and running without having to deploy a large number of people in that space. Next slide. With that backdrop, I'm just going to pass it on to Hoda, who's going to talk to you a little bit about IoT data. Again, we're simplifying a lot of different concepts because it's only half an hour, and we just want to demonstrate the process and the methodology, and let's stay focused on that as opposed to actually executing the code. So with that, I'll pass it on to Hoda on the IoT data extract. Thank you.
Thank you, Babak. Just a little bit of the background of IoT. What we call IoT, and what are the applications in the oil and gas? So IoT is a network of physical objects connected to the internet. They come in the form of different sensors. We see them on the tanks, on our pumps, on the pipelines, like on our drilling rigs. They come in the format of wearables and also drones. And they have many applications in the oil and gas when it comes to supply chain management, pipeline monitoring, for leak detections, for production optimization, drilling management, predictive maintenance, which is a big application of this, like these IoT data. And they impact our risks positively. So they reduce risk. We can use this data to reduce the cost of our operations and maintenance by eliminating unplanned maintenance and reducing the downtime. When it comes to ESG efforts, it actually accelerates this process with increasing safety and reducing the environmental impact. But this data comes with challenges when it comes to generating insight and doing analytics, which I'm going to talk about in the next slide. Next slide, please, Sylvia. And then because this data comes at really high volume, it's continuous, it comes real time, and it comes from multiple sources and from at different frequencies. And that makes it challenging for generating insights and doing analytics on this data. We need effective data management systems that can handle real-time data. We need powerful technologies and infrastructure to be able to process this data, and specialized in a combination of data and analytics skills to be able to generate insights from IoT data in a cost and time-effective manner. So the challenges, as I mentioned, are in the data management. We need different systems of storage for this real-time and continuous data. We need processing capabilities, and that brings the technology management, which we have to manage the cost to process this data, and the infrastructure that has to be powerful enough to handle this amount of data. Also, there are a combination of techniques and advanced analytics that are required to effectively generate insights from IoT data and put it into the context of business. We need to have knowledge of time series analysis, handling high frequency data, be able to run the predictions and anomaly detections on this high volume data, and bring in the industry know-how to actually generate value from what we do on the analytics. And with that, I'm going to hand it to Sylvia to actually show you how we use our platform Digital Hub and our expertise and experience in the oil and gas projects to actually remove these roadblocks when it comes to IoT analytics. To you, Sylvia.
Thank you, Hoda. So now we're actually going into the use case dealing with this IoT data. So what we have is an open data set from a hydraulic system. And then so that hydraulic system, it has a total of 2,204 cycles, in which all of these cycles, they come in a lot of many different sensors. So then there is sensors on temperature, there's sensors on vibrations, sensors on pressures, and then all of these sensor data, they actually are a text file. So this is actually very similar to real life. Maybe we'll get the data produced from these sensors in unformatted text files. And then what we'll have to do then is to then ingest these text files into a format that we can start to do analysis on. And then because as Hoda mentioned, a lot of these text files that comes in, the sensors they produce the data in very high frequencies. So then we also have to process these high frequency data into a format that is going to be usable and actually processable in our algorithm and in our machines. So then in this process, after in a very high level, we'll go through ingestions. After we get the data, we'll go through some rank coding and visualizations where we actually try to unify the frequencies. The frequencies, they may come in, some sensors produce them at 1 Hertz, some sensors produce them at 10 Hertz, some sensors produce them at 100 Hertz. So we have to unify all of these frequencies together, do some errors handling, and also handle some outliers, visualize them a bit to look for different correlations and how these sensors are, how the pumps are behaving with these sensors. And then the next process then will start to get ready to put them into a clustering algorithm. So then like this use case here, what we're trying to do is to have a clustering algorithm in which it can help us detect cycles that is anomalous. So then cycles that is behaving weirdly, and then so we want to know what cycles are going to be an outliers outside of the normal range, and then know why these are marked as outliers. So that in preparation for that, since we're clustering cycles as our finest granularity, we'll have to aggregate our hydraulics sensors data into a observation where it's one cycle per observations, and then also generate some different features that might help our cluster perform better, maybe some correlations, and also some feature selections. And then at the end, when we actually put the model out for deployment, then we can have real-time management of the model and the real-time monitoring and alerting And then as we gain more insight and more information into the hydraulic pump itself, then like we might actually be able to develop ensemble modeling that can help us give even better results. So that's just in very high level the entire process of how we're going to be going through this use case. So then now looking into the data a little bit more itself. So what you see on the graph here is actually a summarized data, the summarized trend of how each of these sensors looks like throughout the 2000 cycles that we have in our data set. So then taking the median of every single cycle in these sensors and plotted them out across the cycles, just to see how this hydraulic pump has been behaving overall. So then you can kind of see there's three major phases in here, where the first phase, there seems to be a lot of fluctuations, and there are some transition phases in here as well. So then now what we're going to do in terms of the preparations is some of the features that we have extracted. So just from looking at this graph here, what we have actually decided to do is that these features, how we're aggregating them, such that we have one hydraulic cycle per observations for the clustering, is that we're taking the median and the cycle ranges for each of these sensors for each cycle. And then what we have done additionally, just from looking at the graph here, we've noticed there are some very high correlations in between some of these sensors. So for instance, volume flow, so FS1, and the pressure sensor 1, TS1, there seems to be quite a bit of correlations between them. So some of the feature engineering that we did is that we have taken the correlation factor between these two cycles. So then anything that is just from common sense here, if it's a normal cycle, they should have very high correlation with each other. If the correlations are decreasing in some cycles, maybe that's a cycle that is going to be an outlier. So that's just in general what we have done with our feature sets here. And because our final purpose on this use case is that we'll be able to take in data that is real-time streaming into the system and then do a clustering on them to decide to detect whether it's a normal or anomalous cycle. So then we'll split up our data sets here into a training set and a validation set in which we're going to imitate the situations where we're training on data we've seen before, and then future data are coming in, and then we wanted to see if it's actually going to cluster these cycles properly. So that's overall in terms of the data preparations, and then all the feature engineering that was going in into the cycle, into the clustering algorithm. So now on the slide here, what you're going to see is the graph here, very similar, so in the same trends for these sensors here, but now instead what you're seeing with the colors is that the red color are all of the cycles that is clustered as abnormal or is an outlier outside of the normal range. So how we got to this is actually we have developed we've tested out 4 different outlier detection clustering models on the training set, in which there were 2 that showed very good results on the validation set and was able to cluster a little bit better with the normal range, where the normal ranges are. And so that was EP scan and elliptical envelope. So these were the 2 algorithms that came out best. But we started to go with the elliptical envelope because that is the algorithm that's going to give us a little bit more on that prediction capabilities. So overall, there is 170 cycles that is marked as outliers, so anomalous, out of the 2000 cycles from training sets. Generally, we see them in the transition phases between one phase to another, and also like a lot inside that fluctuation phase inside the phase 1 there. So, but there, just from seeing on the graph here, we don't really see any sort of big long interval of anomalous behavior, but they're just really just scattered all over the place. So this is a very high level general view of the results that we get back from the clustering. But now what we want to do is actually get more insights into the clustering itself. So what makes a cycle an outlier? So how does that clustering algorithm perform, and why it decides it to be anomalous? So with that, what we actually have to do before we know why something is not normal is that we have to know what is normal. So what we did is that we took all of the cycles that was clustered as normal inside the training sets there, normalized all the values inside all of the different cycles for the sensors between 0 and 1. So then we just get insights into the trend itself, but not so much on the actual value of the sensor data, but because we're just interested in the trend itself. So then like after aggregating all the cycles together, then we calculated for every single time point inside that cycle, the 12.5 quantile, the median, and the 87.5 quantile. So for every single time point inside that cycle for that sensor. So for instance, what you see here on the graphs here, so say for temperature, TS1 here, what you see on the orange line there, those are the quantiles. So then all of the areas between these orange line, that's going to be our 75% quantile. So that's going to be the range in which we're going to consider as normal for the cycle for the temperature. The red line there is then like the median, so that kind of gives us a representation of where that normal cycle is going to be. But like overall, we've done this for all of the sensors so that we get it for every single sensor. How does the cycle looks like for that sensor and what is considered normal? So now we have an idea of what the normal is. Now we can actually put it in with the outlier cycle itself. So this one is an example of a cycle that is inside the training set that's classified as abnormal. What you see here with the time plot out on the long, out on the left here, the green part is going to be what similarly you saw in the previous slide. So that is the normal ranges that we're considering. And then so the orange line there is the actual cycle, how that cycle actually looks like for this outlier cycle. So particularly for this one, we can see that like it's deviating from the normal in terms of the temperature, the pressure, the volume, and the vibrations. So then like this was a case where like everything was just kind of away from the normal. So then it was classified as an outlier behavior. So on the graphs here on the right, where it's the neighboring cycles, what's that showing? Because the time plot was plotted on a normalized scale. So in this case, I'm plotting out the actual median of that cycle. So then like the red points here is cycle 678. So the median of that in the temperature, and then how the temperature median looks like for the cycles that was preceding it and that follows it. So just kind of get an idea of where that cycle lays in terms of the environments around it. So that was for a cycle that was inside the training set. So similarly for a cycle that we can take a look on the validation set here, what we're actually seeing is that the cycle is being characterized as abnormal just from one pressure sensor itself that's really deviating away from that normal range. So in this case, we can see that the outlier here where the median of this pressure is just generally deviating from normal. This pressure sensor here where everything is just seems to be around 0. So now this one is abnormal because it's deviating very largely away from 0. So these are just a few examples in which how we can get a little bit more insights into why a cycle is considered abnormal inside our cluster. Now we can start to apply some of more professional knowledge onto it and get even more insights and then values out of these here. So this is just in general, the clustering algorithm and what we can do with IoT data in terms of detecting abnormal behaviors. Going into an actual deployment of what we can do with a customer model like this is that we can start to now integrate it with monitoring and alerting. So then putting it with a time series dashboard in which that as real-time data comes in and get processed, you can get alerts on any anomalies that is detected throughout time and then on a real-time basis. And as I've mentioned also before, we can also do a little bit more of a model ensembling. So as you see more of these cycles comes in, you can actually decide for yourself whether like when the algorithms say it was a abnormal cycle, now you can go in and say, is it actually abnormal or not? So then applying some of more of these labels to it now, after getting a little bit more of that data set and with some knowledge on there, we can actually put together an ensemble model where we integrate the clustering with a supervised learning model for even more accurate results. And then so for model management as well, just as new data comes in, you're able to retrain that cluster, recluster on your data sets there to make that model even more relevant to your current operating environment and make any changes that you make to operating environment to make your algorithm grow as you grow with your operations. So that is in general the use case that we have done on the IoT data here. And then so I would hand this back to Babak for any of the closing remarks.
Thank you, Sylvia, and thanks everyone for sticking around. This was a really high level, but the details of the code and the execution of it are on Digital Hub. You can review it. You can sign up and see the code. And this was specifically on a hydraulic pump. This methodology can apply to a number of different domains, pipeline integrity. There were some questions around corrosion detection. These techniques are universal. Understanding what is the normal behavior of your asset and when does an anomalous behavior happen. It's what machines are very good at. And as you start to go down this journey of using machines and machine learning to identify anomalies and detect areas that you could improve, you will see that this is a fantastic and very exciting area to leverage data that you already have to generate new business outcomes and possibly use cases. We do have excessive experience in pipeline integrity, simulations of probability of failure of a pipeline, optimizing the outputs of the pipeline, etc., etc. There were some questions, so I just want to highlight that. But do reach out to Hoda or myself on LinkedIn for other use cases and see if there's something that is applicable to you. We are always happy to share with you. Our next upcoming webinar is on October 26th. We'll be following on the same topics, and you can contact us, like I said, to see if you have an exact same use case or similar use case, and you just want to learn how to go about it. We're happy to offer some of the insights that will set you up for success, because ultimately this whole space needs to grow. We need to grow together, and if you're successful, then more people will start doing machine learning and artificial intelligence applications in their business units. If you are interested in the platform itself to explore and see how Digital Hub can accelerate your next project, there is a promo code that gives you 40 hours of free usage every month. Please use that, take advantage of it, and you can go to cloud.digitalhub.io to subscribe for a plan. With that, I just want to thank everyone again for your time. I know everybody's busy. We have a very quick survey. We have dramatically changed our format of this event. Please let us know if how did you like this event, and we'll go from there. Thank you very much again, and I hope we have a wonderful